So this is the second semester Cram movie, the 2022 edition. Don't you dare put this on double speed. Listen to it at regular speed, and hopefully this will help you get through that practice exam that we went through. Let's get started. I just want to remind you that we've got our exam outline, and we're going to do this over 2 days. Here's the schedule for the first day. We've got the 7 problems here. I'll run through the examples on those, and then we'll get to the second day. So let's just dive in. You have access to this document through Google Classroom, so I don't need to stay on this too long. So for the first 2 problems, we're simply doing antiderivatives, right? Indefinite integrals. So I'm going to use the power rule on this first problem. I'll kind of split the screen into 2 parts here. And this is going to be negative 18x to the 6th over 6th minus 20x to the 5th over 5 minus 4x to the negative 6 over negative 6, and then plus c. Oops, I just screwed up there. Yep, that's a common mistake. I was doing derivatives instead of antiderivatives. Negative 5 plus 1 is negative 4. Don't curse me out on that one. And listen, just like every other math class you have in high school, we want to simplify these answers. So like negative 18 divided by 6, that's 3. So this is negative 3x to the 6th. And then 20 divided by 5 is negative 4x to the 5th. And then negative 4 divided by negative 4 is positive 1. And I'm going to make that 1 over x to the 4th just because, you know, we don't like those negative exponents. And then I'll put the plus c on the end. And that should be what the answer key says the final answer is. So there's our first indefinite integral there with a plus c at the end. Don't forget the constant c. Let's move quickly over to the next problem. And hopefully when you see this one, you should be thinking composition, because we've got this expression that's plugged into this cubed function. And so what I'm going to do is u substitution. Let me remind you that u substitution looks like this. You choose u, and u is going to be 3x cubed minus 4. We do the derivative, du over dx, and that's going to be 9x squared, and then we solve for dx, and that's going to be du over 9x squared. Once you do that, you want to make a new indefinite integral. So the new indefinite integral is going to look like this. The 9x squared, we haven't dealt with that yet. The u is on the bottom, and it's cubed, so I'm going to put the u in. And then instead of dx, I'm going to put du over 9x squared. Okay? And we do that so that we can change this from an x problem into a u problem. Now, notice, oops, that's a 9 down there. It's 9x squared, not dx squared, 9x squared. This only works if all the x stuff cancels, and in this case it does. So I have this new antiderivative, an indefinite integral of 1 over u cubed. I'm going to write that as u to the negative 3 so I can do my power rule. And that's going to be u to the negative 2 over negative 2 plus c. And then for indefinite integrals, right, up here we don't have the little numbers, we put u back in for our final answer. So this is going to end up equaling, I'll put it in green like the other one. I'm going to make this negative 1/2 for the negative 2 in the denominator. Actually, let's do it this way. Let's write it as a fraction. That's probably what the answer key is going to show. So let's make it negative 1 over 2, and then u was 3x cubed minus 4, and that's going to be squared in the denominator, and then plus c is over here. I squeezed it in there at the bottom of the video, left-hand corner there, but you can see that we did our u substitution and knocked it out there. So this down here is our final answer for that one. For the rest of the video, I'll try and do 1 problem per screen so that I'm not squishing everything in like I did on this one. But these are both very doable problems, like basic antiderivative type problems that everybody should be comfortable with. We will continue to practice, so if it felt rusty, don't panic. You're going to remember this. It's going to come back to you. Let's move on to the next one. So for problem 3, like it says in our outline, we're going to do what we call an initial value problem. And basically with an initial value problem, you want to do the antiderivative and then use the initial condition to solve for c. So that's what we're going to do. whatever the derivative is that you're given, just pop it into an indefinite integral. So we're going to do the antiderivative of cosine of x. And when I do the antiderivative, excuse me, that's a negative cosine x. When I do the antiderivative here, that's going to actually be negative sine of x. Right? We're going backwards from a negative cosine, so that would be a negative sine. Then there's a plus c. Now what people often forget is that this is actually f of x. So it's f of x equals negative sine of x plus c, right? This was the derivative. This was f prime of x, and when you do the antiderivative, you get f of x. But they differ by a constant. Now, what we're going to do is we're going to use the initial condition here of 0, negative 2 to finish this off. So we're going to put negative 2 where the y value, or the f of x value is, and we're going to put 0 where the x value is, and we're going to solve for c. Now, I know how much you resisted learning the unit circle, but everybody should know the sign of 0, even if you don't know the unit circle. The sign of 0 is 0, and so we end up with negative 2 equals 0 plus c, and that says that c is negative 2. So we've found the value of c. Now we just have to write out the actual function. The particular solution is the function. So we're going to write f of x equals negative sine of x minus 2. This is the particular solution that goes through the point 0, negative 2. There's a whole bunch of other solutions that don't go through that point, but this is the one that goes through 0, negative 2. All right, let's move on. Now remember, as you're working through this video, you can always pause at any point and you can write down questions so that we can talk about them in class. But in general, I'm just going to keep rolling because it's going to be a long video. And I want to get to that track meet so I can see everybody participating in the Metro League Championship. Okay, so this is a definite integral, meaning that we're going to do our antiderivative and then use the fundamental theorem to get the value. This has a number for its answer. And I can already hear you freaking out because of the fractions, but listen, fractions are just numbers and we're going to deal with them. This is not a composition, so we don't need to do u substitution. We're going to do the power rule on these things. Okay, so let's knock out the antiderivative. That's going to be x cubed over 3, but times 2, so that's 6, plus 3x squared over 2, plus 7x over 2. And we're going to evaluate that from negative 3 to 1. So, oops. When I substitute the 1 in first, you do 1 first, then you do negative 3. I get 1 over 6 plus 3 over 2 plus 7 over 2. And then you put in the negative 3, and I get negative 27. Where's my ink here? Sorry. Negative 27 over 6 plus 27 over 2, right? When you square it, it's positive 9. And then minus 21 over 2. That's over 2, sorry. My microphone's still working? Yes, it is. All right. It's been glitchy, so I got to check every once in a while. Okay, let's see if we can figure this out. I've got 1/6 plus 27/6. That's 28/6. And that reduces to 14 over 3. So I'm going to erase that and put 14 over 3. Sorry about that. I'm just trying to keep it simple here. 14 over 3. All right. And then let's look at these guys. So this is 10 over 2, which is 5. And this is 6 over 2, which is 3. So that's a total of 8. Is that plus or minus? That's plus. So that's going to be, so I made a mistake somewhere. What did I do here? This is 10 over 2, which is 5. And this is, oh, I forgot to distribute. Hold on. My bad, my bad. I'm going to get it. So let's go back to this. This is 6 over 2. This is 3, but remember, we're subtracting. So this is actually negative 3. And so that means 5 minus 3 is 2. So this is plus 2, which is 6 over 3. And so that is 20 over 3. Let's put that in green because that's the final answer. Whew! Fractions are tough, but we can handle it. All right? 20 over 3 with no calculator. You can do this. All right, next on number 5, we're doing another definite integral. Notice this is a composition, right? The 2x plus 3 was plugged into an x squared there, a u squared. So I'm going to say u equals 2x squared plus 3. The derivative is 4x. And when I solve for dx, I get du over 4x. And remember, for definite integrals with u substitution, we stay with u because u is good. So I'm going to do u of 1 and get 5, and u of 0 and get 3. So my new definite integral is going to be, oh, that's a terrible integral sign, but we got to keep rolling here, between 3 and 5 there, of, we're plugging, there's a 12x on top. On the bottom, it's u squared, right? And then dx becomes du over 4x. So the 4x and the 12x are going to cancel, but there's a 3 left over, so don't forget that. The actual problem that we're going to compute is 3 times the definite integral from 3 to 5 of u to the negative 2 du. And that, when we add 1, I'm not going to make this mistake again, so this is going to be negative u to the negative 1, which is negative 1 over u. And we'll compute that from 3 to 5. Don't forget we had to multiply by 3, so I'm actually going to put a 3 on top here. It's negative 3 over u. So that's negative 3/5 minus negative 1. So that's going to be, what is that, 2/5? Yeah, that's 2/5. Excellent. Okay. So there is the answer on that one, 2/5. Just remember with u substitution, you choose u, you take the derivative, solve for dx, and then because this is a definite integral with numbers around or on the integration symbol, we're going to convert those. Stay with u so that u is good, or because u is good. You know what I mean. All right, next problem. Okay, so we're given capital F of x, and we're asked to find the derivative of capital F of x. And this is, even in the hint that I gave on the study guide there, it said, remember that this is just the first fundamental theorem of calculus. So our job is to take this thing, as long as there's a number on the bottom, we take this thing and we put it where t is. And I'm going to simplify. And then don't forget, because this is a function of x, I have to multiply by 3x squared, right? The chain rule when I'm done. So here's what it's going to look like. It's going to be negative x cubed minus 5 x cubed squared minus 3 times x cubed plus 4, and all of that is going to be multiplied by 3x squared, the derivative of x cubed. So now it's just a matter of algebra and exponent rules. So this is going to be negative x to the 9th minus 5x to the 6th minus 3x cubed. That's a terrible looking 3. Let me fix that real quick. Plus 4, and then we're going to distribute this 3x squared. So what are we talking here? Negative 3x to the 11th minus 15x to the 8th minus 9, that's a 9, x to the 5th plus 12x squared. And that'll do it. Okay? So you plug in that top limit there, the x cubed, right, the thing that's in the b position. You plug it in where t is, but if it's not x, you have to multiply by the derivative of x cubed, or whatever it happens to be, the derivative of u. You could multiply by the derivative of x as well, but it's just 1, so it doesn't change the value. But this is a key that people forget. That's the doggone chain rule. Okay, next slide. So this one's more than likely going to be the free response problem. We are asked to find the area under the curve, right, over the interval. So the curve is this negative secant x tangent x, and we're going from negative pi to 3 pi over 4. So it's a unit circle type situation here. Basically, the problem looks something like this. So you put your limits of integration in. The function that we're going to integrate is negative secant of x times tangent of x. And the first thing we need is the antiderivative. So the derivative of secant x is secant tangent. So the derivative of negative secant x is negative secant tangent x. So the antiderivative of what we have here is just negative secant of x. Okay, and we're going to evaluate that from negative pi to negative 3 pi over 4. So we're going to plug in this one first and then this one. Now, unit circle wise, let's figure this out. Negative 3 pi over 4 is over here. The coordinates are negative square root of 2 over 2, comma square root of 2 over 2. We need the reciprocal of the cosine, which is the x coordinate. So we need negative 2 over the square root of 2, which is negative square root of 2. But it's negative of that, so that's positive. Okay, so positive square root of 2 is what you get when you do the negative of negative square root of 2. Then we need a minus sign. Now we're going to plug in negative pi. And remember that pi is over here at coordinates negative 1, comma 0. The reciprocal of negative 1 is negative 1. But we're going to minus a negative 1, so that ends up being the square root of 2. Hold on a minute. We're going to do minus negative 1. So there's a minus here, but then there's also a minus in the fundamental theorem, so that's going to be plus. That's going to be crap. Excuse me. It's going to be minus, which is minus 1, which is negative, right? So this is the final thing. Holy smokers. Square root of 2 minus 1. Be careful with your negatives. There's a negative in the coordinate. There's a negative in the antiderivative, and there's a negative in the fundamental theorem. That's 3 negatives. So I do have it correct, even though I sounded very crazy as I was writing it down. To correctly write it here, this should be a plus sign because there's 2 minuses there. Okay, so that's the end of day 1. Like I said, most likely this area under the curve problem will be the free response problem. So take care when you're writing that out. And we'll practice other versions of this problem before we take the real one. Let's take a quick look at day 2 and then we'll get on with those problems. So here's the plan for day 2. It's in the outline. I want to make a note of this one right here because that's our newest content, right? Integration by parts. And then, of course, everybody's favorite from the AP test, an accumulation application. Don't panic. We're going to practice and you're going to do great. Let's get going. So we're asked here to approximate the area under the curve using 4 left endpoint rectangles. It might help to have an idea of what this function looks like, and you don't need a huge idea, but it's a parabola, right? It's opening upward, and there's some extra junk there, but the bottom line is that it's going to look something like this, and we're going to go from negative 1 to 3, and we're going to have some rectangles in there. We're going to have 4 rectangles. What we need to do is partition this interval from negative 1 to 3. Remember, the way we do that is we figure out what delta x is. Delta x is going to be b minus a over n. So that's going to be 3 minus negative 1 over 4. 4 over 4 is 1. So we're going to basically go negative 1, 0, 1, 2, and 3 for our interval. Since we are using the left endpoint, we are going to start with negative 1, and we're not going to use 3. So the partition ends up being negative 1, 0, 1, and 2. Those are the x coordinates. The function values are what you get when you plug in those coordinates, right? That's how we figure out how tall our rectangles are. This picture may not be completely accurate, but the bottom line is we're just going to add up 4 rectangles, so I just need to know the height because the width is always 1. Okay, so let's compute the heights. Negative 1 squared is 1/2 plus 1, that's 1.5, plus 2, that's 3.5, that's 7 over 2. When I plug in 0, I get 2. When I plug in positive 1, oh wait, I made a mistake here. This one's going to be 7 over 2, but when I plug in negative 1, that's not a positive 1, it's a negative 1, so I got to redo my calculation here. Negative 1 squared is positive 1, so it's 1/2, but it's minus 1 plus 2, so that's going to be 3 over 2. 1.5, not 3.5. And then when I plug a 2 in there, I get 4 over 2, which is 2 plus 2 plus 2, that's 6. So our area is going to be 1 times 3 over 2 plus 1 times 2 plus 1 times 7 over 2 plus 1 times 6. So I'm going to factor the 1 out, and it's just going to be 3 over 2 plus 2 plus 7 over 2 plus 6. This is going to be 8 plus, what is that, 5? So that 8 plus 5 is 13. So 13 units when you add up the rectangles. Did I get it right? Ah, by golly, I did. Okay. So that's the first by golly of the video at 2 minutes and 48 seconds into the, what are we on, the 10th slide. So just make a note of that. All right, let's keep it going. For this problem, we want to find the area of the region enclosed by the curves. In other words, the area between the curves, right? And so essentially we need a quick little sketch of this. And it doesn't have to be perfect, but remember you have a calculator available so you can graph this thing. But I'm just going to go with what I know, which is that y equals 3 goes through up here, and negative 1 over x squared goes something like this, and we're going from 1 to 3, so we're basically trying to find this region. The point is that the 3 is on top and the negative 1 over x squared is on bottom. So we integrate top minus bottom. So that's going to be the integral of 3 minus the negative 1 over x squared, which is 3 plus 1 over x squared dx. And we're going to compute that from 1 to 3. And because you have your calculator available, you can knock this thing out with the graphing calculator. So when you run this through Math 9 with the interval from 1 to 3, you should get 6.6 repeating. And it's 20 over 3, but we're doing it with a calculator, so 6.6 repeating is perfectly fine. Okay, 6.667 if you're doing the AP calculus rules, rounding to the thousandth. Okay. So get a quick picture of your region, but then once you write out the definite integral, you can knock it out with the graphing calculator. I'll probably have a box for you to write the definite integral in, but then I really just want to see the value. Okay, that's enough of that. Let's move on to the next. So I'm showing both problems here, 3 and 4, but I'm just going to do one on this slide, and I'll do another one on the next slide. So these are volume questions, right? We're going to do volumes where we rotate or revolve around the x-axis. Again, it's going to help if you have a quick little picture of what these things look like. Negative x squared plus 4, that's a parabola up here, but it's pointing down. Y equals 0 is the x-axis, so that's here. And here's our region. And we're going to go between negative 2 and 1, so actually that's not quite our region. Let me backtrack that. Negative 2 is here, but 1 is going to be about here. So it's like this region in here. All right. The bottom line is that's what we're doing. And then remember, we're rotating that around the x-axis. So when you make that, your cross-section is going to be a disk, right? The boundary is completely touching the axis of revolution. So we're going to use the disk method. We're going to integrate from negative 2 to 1 because we're allowed to do that here. That's what it told us to do. And we just need the radius squared. The radius is just top minus bottom, which is just our negative x squared plus 4 squared dx. Again, we're in the graphing calculator section of the test, so we're going to knock this one out and have it tell us the answer with a Math 9. Actually, before I knock this out with a Math 9, I better stick my pi in there because remember, the volume is the integral of pi times r of x squared dx. So we got to do pi r squared. So don't forget the pi. That'll mess up your calculation. But when I did this correctly, I get 96.133. And that's our volume of this particular solid. We'll attack number 4 on the next slide. Okay, so same picture, but we're doing this region here. And again, it's going to help if you get a picture on your graphing calculator so you can see what this region looks like. Remember, our basic problem is we need to know which one's on top. And between pi over 6 and pi over 2, cosine's positive, so I'm going to assume this one's on top, but please also look at your graph. Okay, so let me just draw a quick sketch of what I see on my graph, and then we'll move on. In the region that we're concerned with, the graphs look like this. The 2 cosine x is up here, and the cosine x is down here. And so we're going to do a region in here. Okay. Actually, they come to a point right here, but since we're starting at pi over 6, we don't make it all the way to the y-axis. So anyway, the way we get that, this is a washer, right? Because there's a gap here. There's this gap between the region and the axis of revolution. We're going around the x-axis. So this is a washer. So when we write this thing out, it's going to be v equals pi times the big R, which is the green one, minus 0. So that's going to be 2 square root of cosine x. Oh goodness, let me erase it. I got to write it so you can read it, otherwise it doesn't help you. 2 square root of cosine x, and that's squared, minus square root of cosine x, and that's squared. And then that's our integrand. I'm sorry that I squished it in there. This is terrible. I should have moved that over. But again, you're just going to crank this thing out and type it on your calculator. Since I wrote it so nasty, I'm going to rewrite it here, but I'll do the squaring. So this is just 4 cosine x minus cosine x dx. And then, shoot, since I'm already here, I'm going to just make that 3 cosine x, right? That's going to end up being the answer when you pop this out. So if you want to make it easier on yourself to type it in, you can simplify this thing, but ultimately our goal is to get the final value, and you're going to use Math 9 again to do that once you get it set up. Of course, don't forget your limits of integration here. I've got a pi over 6 and a pi over 2 and a pi over 6 and a pi over 2 and a pi over 6 and a pi over 2. All right, but when I knock that out, I do get the right answer. It's 4.712 when you do the calculator with decimals on the calculator. The calculation with decimals on the calculator. Something like that. That's what my calculator said. Okay, yeah, I guess I'm starting to get tired as I knock this thing out, but stick with me because we're going to get through these last few problems. Okay, we got to move on to number 5. Let's do that now. This time we're going to use the method of cylindrical shells to get the volume. We're going around the y-axis. And again, it's going to be important for us to get a picture of our region. So graph these two functions, but pay attention to your interval here. We're only concerned with 0 to 1. So when I graph mine, here's what mine looks like. So that negative x squared plus 5, that's up here. We'll call that red. That's my top boundary. And remember, I'm only doing 0 to 1, so that's like this. And then the x squared plus 3, that's here, and it goes like this. And the region that we're rotating is this region. It's going around the y-axis. So we're making some kind of weird ball-shaped thing. Here's the strategy that we've been using for cylindrical shells. We take a typical slice, and that's just a line that's going to end up being the edge of a cylinder, right? So and I'm trying to draw this as best I can, but that's the typical cylinder. And we need 2 measurements. We need the radius, which is the right minus left, from that bar to the axis of revolution. For us, the radius is just x minus 0. Right? It's the right, which is x minus 0. And then we're doing red minus blue for the top minus bottom of the height. The height is top minus bottom. So I'll put that here. The height is going to be the top one, which is negative x squared plus 5, minus the bottom one, which is x squared plus 3. And that simplifies to negative 2x squared plus 2, right? Because I got to distribute this negative sign. So when I write this integral out, I'm going to integrate from 0 to 1. When we do the cylindrical shells method, it's 2 pi times the shell radius times the shell height. And if we've written that out correctly, we could type this in, that's 2 pi, on our graphing calculator and have it do the calculation for us. When I do that, I come out with 3.1415926. That's just pi, right? It's going to be 3.142 if you're rounding it off. But that's the answer that we get when we knock this thing out, and that's the correct answer. So please remember that method of shells, right? We need that vertical bar that we're going to make the cylinder out of. We need the radius. If you're going around the y-axis, it's just x, all right? If it's not the y-axis, you have to do right minus left. It's always x minus the axis of revolution. Or if the axis is on the other side, it's axis minus x. And the height's always top minus bottom. So that's our cylindrical shells. You can go back and look at the other videos and sample problems that we did when we studied that if you need more examples. Let's move on to the next problem. We're close. Okay, so number 6 is asking us to find the general solution to the differential equation. Whoopsie, I just made a movement there. Differential equation. And the only kind we know how to solve are separable differential equations. So essentially all I'm going to do is get the y stuff on the left and the x stuff on the right, and then I'll solve for y. So we have dy over dx equals 2x e to the y. We are going to multiply e to the y over the other side, so we'll have e to the y dy, and we'll multiply dx, that's a y there, dx over there, and that's 2x dx. That's called separating the variables, and then our technique is to integrate both sides. So we're going to do antiderivatives. The antiderivative of e to the y is just e to the y. Now remember there's a plus c, but we're just going to combine it with the plus c on the right. The antiderivative of 2x is x squared, and then there's that plus c there. Now to solve an e to the y problem, we use natural logs. So I'm just going to do the natural log over here, and I'm going to end up with y equals the natural log of whatever x squared plus c is. And we're done. That is separable differential equations. The general solution is the equation that has the c in it. Right, that's what they mean by general solution. When it says particular solution, that's when they want you to solve for c, like we did back in, I think it was problem 3. Particular solution means solve for c. General solution means get your equation, leave the c in there, and move on. And that's what we're going to do now. Okay, we're almost there. For problem 7, you know ahead of time this is going to be an integration by parts problem. It doesn't specifically say it, it just says find the indefinite integral, but this is the type of problem that we can't do without integration by parts. It's a form of a product, it's actually a quotient, but it's a form of a product, and that's a trigger to let you know that you might need integration by parts. Now, when we do integration by parts, we need to pick out a u, and I have told you several times that whenever there's a log of x in your equation, choose that for u. So I'm going to choose u equals log x. And that means dv is everything else. So it's a 1 over the square root of x dx. Now I'm going to write that as dv equals x to the negative 1/2 dx. Then the strategy continues. Do the derivative of u. So we're going to get du over dx equals 1 over x. And I'm going to multiply by dx to solve for du. On the green side, I'm going to do the antiderivative so I can figure out what v is. The antiderivative is going to be 2x to the 1/2, right? Because I add 1 to negative 1/2, and I get 1/2, I divide by 1/2, which is multiplying by 2. Now, these are the pieces we need. We need u, oops, I guess that's okay. We need du, and we need v. Here's why we need those. The integration by parts formula, in case you've forgotten, is the integral of u dv equals u times v minus the integral of v du. So we need to fill in these blanks. We need to fill in u, v, and du. And we have those three here. Okay? So let's write it out and see what we come up with. The integral, right, which is log x over the square root of x dx equals u times v. Now I'm going to write it like this just so it's easier to see. I'm going to write 2 square root of x. Let me get rid of that x there for a second. 2 square root of x times natural log of x. This is the u and this is the v. So that's u times v minus the integral of 2 x to the 1/2 times 1 over x dx. That's the v du. And now I need to evaluate this so I can finish this off. Okay. Before I do that, let's rewrite this a little. 2x to the 1/2. This is actually x to the negative 1. So let's just make this x to the negative 1, right? And then we can just do our rules for exponents. That's going to be x to the negative 1/2 because I'm going to add those together, right? So this really is 2x to the negative 1/2. And I'm going to do the antiderivative, which I basically already have done, except I got an extra 2 in here. So this is just going to be minus 4 square root of x, or x to the 1/2, and then plus c. So the final answer is this uv stuff that we had over here, and then the antiderivative of 2x to the negative 1/2 is 4x to the 1/2, which is just 4 square root of x. And so now we've got our solution here. 2 square root of x log x minus 4 square root of x plus c. All right, we made it. We've got one more to go. Let's knock this thing out. So in our outline, I sort of gave it away that this was going to be an accumulation problem, and you can guess that this is also going to be our free response problem. So let's see what we're given here. We're given a derivative. The derivative f prime of x is sine of x squared. And we're given an initial condition for the function x, which is f of pi equals 8. The first thing we're asked to do is write a formula for f of x, and then we're supposed to plug 10 into the formula and round to the nearest thousandth. And we can use our calculator for that part b. Let me remind you about our accumulation formula. Our accumulation formula looks something like this. F of x equals f of a plus the integral from a to x of f prime of t dt. Right? That's what we're supposed to fill in. And essentially, our main job is to figure out what a is and what f of a is. And the good news is those are given to us. A is the number in the parentheses there, which happens to be pi, right? This is a, and f of a is 8. So when I'm writing out my formula, I'm simply going to put for letter A, f of x equals 8 plus the definite integral from pi to x of sine of, and I'm going to put t squared instead of x squared because it's supposed to be a different variable than the x, right? So we want f of t dt. So just change the letter right there. Now we've got our formula. And then all you have to do on your calculator is type in what f of 10 would be. F of 10 is going to be, and you'll type this in your calculator, 8 plus definite integral, so math 9, pi to 10 of sine of, you can use whatever letter you want now. You can do sine of x squared if you want, dx, when you type it in. And you'll type that in on your calculator and you'll get a value. So here's what my calculator said. I'm getting 7.811 to the nearest thousandth. Okay? So that is the y value for 10, 7.811. The y value for pi is 8, and the y value for 10 is 7.811. That's accumulation. There should be a song about that, but I don't know it, so I'm not singing it. Okay, listen. You got a lot to remember and practice between now and the exam, but this is doable. Just take it one at a time and be good at the ones you're good at, and then we'll fake it through the rest of them. All right? Please give this a view. Obviously, you're at the end of the movie, so you probably saw it. Tell you what, +1 on the exam, +1 on the exam right now if you send me a Google chat or a remind letting me know that you made it there. Just say, dude, I watched the whole video. I want my +1. Okay? +1 on the exam. Okay. Good luck, and I'll see you soon.